Okay, in this video we are going to introduce the application that's called the mass spring oscillator. So this is the content in section 2.4, and mass spring oscillators are a really natural application where the differential equations that we've been studying in this chapter arise. So let's first just explain what this system looks like, and then we can talk about the physics behind it and then derive the equations of motion for such systems. And so here we've got a mass, m, which is attached to a spring. That's what this thing is, and that spring is attached to, say, a stationary wall over here. And what we want to do is we want to see what happens when we take this mass and either pull it in this direction and let it go, or say squish it in this direction and let it go. And as time goes on, as you would suspect, the mass is going to kind of oscillate back and forth, possibly. And so to derive the equations of motion for this system, we're just going to use the typical rule in physics that the forces that are acting on the spring should equal the force exerted by the spring. So let's first just think about what are the forces that are going to be exerted on the spring. On the mass. And so one force is going to be the force which is due to the spring. And so the physics behind that is what's called Hooke's law. And so Hooke's law says that the force exerted on the mass by the spring, that is proportional to the displacement x. So x, I should say, is denoting how far the mass has been moved from its equilibrium position. So here would be its equilibrium position. If we pull it to the right a little bit, then x would be positive. And if we push it in, then we're going to assign a negative value to x. And so what this law is saying is that the force exerted by this spring becomes more and more and more the further that x is displaced from its equilibrium. So if x were a really big value, positive, then that spring would want to whip it back pretty quickly. And if x was a pretty large negative number, so large in the negative sense, and we squish this in really far, then the spring would exert a big force to shoot it back out the other way. So one force that is exerted on the mass would be the force due to the spring, and that's determined by Hooke's law. The next force and the only other force that's being exerted on this mass is the force due to the friction. And so this mass is rotating back and forth over this surface, and depending on what the surface is, there's going to be some friction. And the force due to the friction is dependent not on the position x, but on the velocity x prime. And so the faster this mass is moving, the more significant the effect of friction is going to be. So the larger that x prime is, the larger this force is. So we've got two forces acting on the mass. So I'll denote these two being exerted on the mass. And then the force that is being created due to the motion of the mass that we get from Newton's second law. And so Newton's second law says that the force generated by this mass is equal to the mass of the spring times x double prime times its acceleration. So we've got this being exerted on the spring, the mass spring, and this is what's being exerted by the mass spring. So at the end of the day, we need to have these forces balance out. So the force being exerted by the mass should equal the force being exerted on the spring. So that would be the minus bx prime from the friction minus the kx from the spring. And that's what's called Hooke's law. And so if we were to group all of these terms on the same side, bring this over here, then we can rewrite the equations for the dynamics, for the motion of this mass spring oscillator. And that's what we have down here. So that's why this is a really classical example to look at when we're studying second order linear differential equations with constant coefficients. So here the m and the k and the b, all of these are constants. The m is the mass. The k is related to the spring, and the b is related to the surface that the mass is rotating over. So these are all at least greater than or equal to 0. And furthermore, I should say that we're going to start looking at what's called the free mass spring oscillator, meaning that there's no other forces acting on this mass. The only forces involved are the forces due to the spring and friction. So on the right side, we have a 0 over here. So we're first going to consider the homogeneous case, and then we'll put some external force on the system and take a look at what resonance might look like in this context. So where we're heading with the next couple of examples is we've studied what solutions look like for these homogeneous systems, and namely, depending on whether the roots of the characteristic equation are real or complex, then that changes the form of what our homogeneous solution will look like. And now we can connect the change in our solutions to what effect those that might have on the behavior of the mass spring. So when our solutions are real, we'll see certain behavior in this system. When our solutions are complex, we might see that the behavior of the mass spring is going to change. So that's what we'll take a look at in the next couple of examples.